Flutube. Get it straight.
Okay, let's look at part 1 of chapter 6. This is a new chapter called Fluid Kinematics, and we're going to look at these little fluid packages right here. And if you want, you can take a look at some of those movies that we looked at earlier, those old-fashioned movies, but they do a good job of showing these visualizations of the things we're going to start learning about in chapter 6. So let's start off with some basic fluid kinematics, and then we'll get on to these other topics. So fluid kinematics are a pretty important part of fluid mechanics. In some cases, you can actually get nice closed form, easy solutions for some special cases that are mainly for laminar flow, but you'll see they're pretty useful, and you can actually solve them with this kinematic approach. But more importantly, probably are these next 2 points where you need to get an understanding of things that have complex systems, complex geometries that are too hard to solve with a pencil and paper. You need to solve them with a computer, and this requires computational fluid dynamics software, CFD. So what are the kinematics things? So kinematics are where we take this element here is shown as a square, but sometimes if we want to go three-dimensional, we have it as a cube. And this element may be feeling a flow field, a velocity field, different velocity vectors. Just draw them kind of generally here, but you could have a variety of velocities in a velocity field, as you know. These things are going to operate on this square and either translate it, just move it unchanged from point A to point B, or potentially it could stretch it, or it could just rotate it without changing its shape, or it could squish it or angularly deform it by coming in from different sides. It really depends on the velocity field. So kinematics is about trying to understand that so that you can work with general types of flow fields. So remember, the velocity field is this expression for the velocity vector, where we have it in terms of a r vector changing with time, and it can change in the x, y, z direction, the velocity that is, and it can also change with time. Same, here's the y direction, z direction. So the position tells you how fast it's changing with respect to the different coordinate systems, and the speed is the magnitude of the velocity vector, so that's just the square root of the sum of the squares of the individual velocity components. So that's all well and good. Now that also, if the velocity is changing out there, then there's got to be an acceleration term as well, right? And the acceleration term, remember, is a little more complicated. We have to take the derivative of the velocity field. We do that, the first term is pretty easy. It's just the derivative with respect to time. But when we do that in terms of different components, we also have the derivative with respect to of the velocity with respect to the x direction times the change in the x direction with time here, which is actually just little u, the velocity in that direction. Similarly, the change in velocity field with respect to y times dy dt, by virtue of the chain rule, where dy dt is little v, velocity in the v direction. So we get these terms carried down here, and as we recall, we have the local acceleration, and these three components are the convective acceleration. So acceleration can happen in a steady state field, remember, by virtue of this convective term. So here's the general expression for the acceleration field. So if we know the velocity field and the acceleration field, we know a lot about fluid motion, but we don't know exactly how things are going to distort as they move through that field. And that's what fluid kinematics is all about. So let's start by looking at this simple case where we have this fluid square here, and it's got feeling one velocity on one side, but potentially feeling a little bit more velocity on the other side. So it's going to tend to stretch and form this bigger unit here. has to, right? Because it's feeling more velocity on one side or the other. Now, if we took a look at this, we could say that the velocity on the outer side is u, velocity on the inner side, plus the change over x times dx. So for the one velocity component in the x direction, the change in volume of this small square or cube would be this change in the velocity times the area, which is dy times dz, times the time over which this was occurring. That would be the change in volume. And we could take a normalized look at the change in volume. So 1 over dv times the change in dv dt would be the limit as dt goes to 0 of this change in velocity, which would just be the derivative. That's, in fact, if you remember way back to your early calculus days, the definition of the derivative is this limit as dt goes to 0 of this term. So with a similar approach, you would get the same looking type of thing in the y and z directions. And if you noticed, you have basically the gradient of the velocity field, the change of u with respect to x, v with respect to y, and w with respect to z, which is del dot v, the vector v. So if we have an incompressible fluid, then the volume change will be 0 because density is constant. So if we look back at this picture, we notice that if we have the same amount of mass in this square and we try to stretch it out, we can't get the same density anymore because there's going to be mass spread out over a greater area or volume if this was a cube. So what this is saying that is if we have an incompressible fluid, then it cannot stretch. An incompressible fluid only moves in one dimension. If it only moves in one dimension, then it's just linear motion. Now, if it moves in more than one direction, then angular motion may occur as well. So, may occur as well. In fact, most of the time it would, unless there were some really special cases where it was non-rotational, and we'll learn about that in a minute. So let's look at angular motion. So angular motion has to do with the velocities of the angles or the sides. How fast, what's the angular velocity of this side? So if we have a velocity down here at O and a dot velocity up here at B, you can see that if O is 0 and B is, or if O is U and B is U plus some change in U, then we end up with a velocity, an angular velocity like so, if the velocity at B is greater than at O. Similarly, if the V component of the velocity is greater at A than at O, then it's going to swing it this way, right? So those would be our angular motions. So if that's happening, then we can see this thing getting squeezed like so. So we can look at these little triangles here, and you see the two sides of the triangle. One is the derivative side over here. One is just simply dy over here. Similarly, we have dx, and we have this more complicated term over here. But if we look at those, we can say that the tangent of that angle that it's changing is just equal to the opposite over the adjacent. So here's the opposite, here's the adjacent. And remember, if tangent gets really small, then you can just say that it's actually the angle, not just the tangent of the angle. And you could do the same thing with the other wall. And you'd end up seeing that these angular velocities are really just equal to the derivatives with respect to the opposite dimension. So when I mean the opposite dimension, I mean that v is the velocity in the y direction, but we're looking at its change with respect to x. U is the velocity in the x direction, but we're looking at its derivative with respect to y. So these are for the angular velocities. So this angular velocity term may look familiar to you. It's actually what you get when you do the cross product. And here is using the convention that the clockwise rotation is positive. So you could do that for all of the different combinations of sides, and you would end up with the field of the rotational vector. The rotational velocity for this is 1/2 times del cross velocity field. So the cross of the velocity field is approximately equal to the rotation vector, or if you take a half in front of it, it's equal to the rotational vector. So here it is, and this is called the curl. Sorry, I think it's the curl of del cross v. My words mixed up here. So the curl of del cross v, that gives you the rotational vector. At some point, someone must have gotten tired of putting this 1/2, so they redefined something called the vorticity. And vorticity is just defined as 2 times the rotation vector. So psi is equal to 2 times omega, which is just equal to the curl of the velocity vector. So when the vorticity equals 0, the flow is said to be irrotational, i.e. it's not rotating. So irrotational means not rotating. So that means these terms are all 0. They cancel each other out. So you can see it again here more explicitly. So when these terms all cancel each other out, that means there is no rotation, so we will get only linear translation. If any of these terms is not equal to 0, then there will be some rotation as the packet moves along. Lastly, let's look at the angular deformation. So angular deformation, the element will actually change shape, and in this case it's going from a nice square into more of a rhombus type thing, like so. The area should be the same. I've drawn this rhombus a little bigger, but the area there should be the same. So this happens when we have rotational velocities that are sort of at odds with one another. We get through it by looking at these angles in the same way. Only now we're defining the rate of angular deformation using gamma dot, and it turns out that that's equal to the sum of these cross derivatives, where again we have the velocity in the y direction derivative with respect to x, and the derivative of the velocity in the x direction with respect to y. So angular deformation does not occur when the rate of angular deformation is equal to 0. In other words, when these are equal and opposite to one another. If they're equal and opposite to one another, then they will not deform. That's the end of part 1, and now we're going to move on to part 2 and look at continuity.